So it looks like here we've got a cyclic process. We've got 4 steps on the pressure volume graph. And it gives us some information about it. It tells us we've got A is constant pressure, B is adiabatic, process C is isothermal, and process D is constant volume. And it says the number of modes per molecule is constant throughout the cycle, so we don't have to worry about that changing. It doesn't tell us how many modes, but maybe we'll be able to find that later. And what are you trying to figure out here? What's the first thing we're trying to find? What's our actual goal in this problem?
Is it not to find out the number of moles?
Yeah, that looks like what we're starting with. Figure out how many moles are involved, because it doesn't actually tell us how much gas is involved here. But we know that during process D from state 4 to state 1, it specifically tells us that's associated with 60 kelvins worth of temperature. So let's start by focusing in on that. Process D, we know this process involves 60 Kelvin delta temperature. So let's start with that. Process D, we know delta temperature is 60 Kelvin. That's given information. And what else do we know about process D?
There's no work done.
Yeah, no work, because how do we know that?
Since it's a vertical line, there's no area under the curve.
Yeah, no area under the curve. And also, what does that mean physically? What's happening, or rather what's not changing if it's just going straight up and down? Yeah, this is constant volume. This is a constant volume or isochoric process. And in any isochoric process, no change in volume means the piston is not moving, so no work is done. Yeah, there's an increase in pressure. Pressure is increasing, so that means temperature is increasing. And we can tell that from the ideal gas law, PV equals nRT. Volume staying constant, and an R, of course, are staying constant. So an increase in pressure directly means an increase in temperature. And let's see if we can tie that together. We know the pressure, in fact, we have initial values for pressure, final values for pressure, and we know the volume the whole time. Pressure initial equals 2, and that's times 10 to the 5th pascals, so 200,000. Pressure final is 3 times 10 to the 5th pascals, so 300,000 pascals. And we also know the volume is 10 times 10 to the negative 3rd cubic meters the whole time. So 10 divided by 1,000 cubic meters. Something really convenient we can use here, though, a very useful conversion we can use. Pascal, in general, pascals times cubic meters is going to be joules. Pascals is the units of measurement for pressure. It can be written as joules per cubic meter. So when you multiply by cubic meters, you just get joules anyway. We're going to look into exactly what pressure is in more detail in 7b. It's essentially the amount of force the gas applies to the walls of the container, force divided by the area of the wall, which means it's usually written as newtons per square meter, force over area. But it turns out that's the same as joules over cubic meters, energy per unit of volume. So if you multiply pascals times cubic meters, you get joules. If you take a look at the units here, though, this is really given in terms of 100,000 pascals and thousandths of a cubic meter. So if we take a look at the units there, if we just multiply, like let's say we were to just multiply 3 times 10, if we wanted to multiply this pressure times this volume, for instance. But that's not just 3, that's 3 times 10 to the 5th pascals. And we also have not just 10, but 10 times 10 to the negative 3 cubic meters. So we got to keep those in mind. When we're multiplying the 3 times the 10, we're actually multiplying 3 times 10 to the 5th pascals times 10 times 10 to the negative 3 cubic meters. The 3 and the 10 you could just multiply as normal, but what do you get if you multiply 10 to the 5th times 10 to the negative 3rd?
10 to the 2?
Yeah. You can just add those exponents, 10 to the 5th, 10 to the negative 3rd becomes 10 to the 2. And then pascals times cubic meters becomes what?
Joules.
Yeah, joules. So this is a very convenient substitution here. Now that we've done this once, the 10 to the 5th pascals times 10 to the negative 3 meters cubed, we don't really need to worry about those anymore. When we're multiplying, we can just multiply the number on this axis and the number on this axis, and then also multiply that by 100 joules. So we don't even need to worry so much about the unit conversions. I can just leave this as 2 times 10 to the 5th pascals and 3 times 10 to the 5th pascals. And likewise, volume is just going to be 10 times 1/1000th of a cubic meter. But we can focus on just the numbers shown and then put on an extra times 100 joules at the end. Any questions on that so far?
Just to make sure you're doing this to find PV.
Yeah, if we're multiplying pressure times volume.
Okay.
And I think we are going to want to do that when we're multiplying pressure times volume because we're trying to find how this relates to temperature. And I think we can use the ideal gas equation for that. We don't know what the temperature is, but we at least know how much it's changing. So let's rewrite the ideal gas law in terms of change. Delta PV equals delta nRT. And usually for delta PV, we'd write that as P final V final minus P initial V initial. But what's not changing during this process?
The volume.
Yeah, which means we don't need to label V initial and V final, it's just V. And since that's the same V, what can we do with that same V in both terms? If you've got the
same value.
Yeah, we can pull that out.
Factor it out.
Exactly. Factor out volume because it's the same volume. We just get delta pressure times volume. In fact, we could even just leave that as delta pressure times the volume. And that's true for any delta. If you've got a delta of a product and one of the factors in that product is a constant multiplier can be pulled out of a delta. Likewise, in delta nRT, what's not changing? Yeah, the N and the R don't change. So we can factor those out and get NR delta T. So the delta pressure times the volume, which is constant, equals N times R times delta temperature. And of those, I think we can know everything except for N. So how would you isolate N here?
It would be delta PV over NR. Oh, I mean over N delta T.
Yeah, delta P times V, and we just divide both sides by R delta T. And I think that should work because then N will be isolated. And I think we have all those values. We can fill these in. Delta pressure, how much is the pressure changing?
It changes from 2 to 3, so it changes 1 times 10 to the 5 pascals.
Yeah, so we've got our plus 1. And yes, it does have a times 10 to the 5th pascals. But we can ignore that because we already know that 10 to the 5th pascals and then 10 to the negative 3 cubic meters will just multiply to 10 squared joules. So we can fill that in at the end. I would just think of the delta pressure as 1 and the volume as 10. And then we can multiply that by 10 to the 2nd joules afterwards. So a change of plus 1 to the pressure times a constant volume of 10 times 10 squared joules to get the units to work out. And then we have divided by, what's the value of R we could use here?
It's 8.134.
Yeah, or Yeah, 8.314. And that's joules per Kelvin mole.
Yeah.
Which is good because that way joules cancel out. And we're also multiplying that by the temperature change. Delta temperature is plus 60 Kelvin. So kelvins and kelvins cancel out. We should end up with moles. So multiplying all that out, we've got 1 times 10 times 100, that's 1,000. Divided by, and then in the denominator, we've got 8.31 times 60. So 1,000 divided by 8.314 times 60 is pretty close to 2. 2.005, but I assume that we would just round that off to 2. 2.0047 for more accuracy. But I'm guessing 2 is probably close enough. So that's how many moles we're dealing with. We've got 2 moles of gas. And of course, that's not going to change in the process because this is presumably a sealed system. We're not allowing any gas to enter or leave. Any questions on that so far?
Looks good. Thank you.
And then it looks like in the next section, part B, we want to focus on process A. So let's take a look at process A here. And in this case, it tells us the heat involved. We want to figure out something about the number of active modes. Any thoughts on how we might proceed there? How could you relate the number of modes to everything we know about process A? What do we know about process A? Other than the given.
I mean, I see that it's a horizontal line, so there's no change in pressure.
Yeah, it's a constant pressure. And yeah, we can use the equation for delta E thermal, especially since what we're specifically trying to find is number of modes per molecule. And using that equation for delta E thermal equals 1/2 times, and we got to be careful about this because 1/2 times number of modes times Kb times delta T. Number of modes per molecule is what we're trying to find. But the thing is, we're not dealing with just one molecule. We're dealing with how many molecules? How would you write out how many molecules this gas consists of?
Maybe 2 moles times Avogadro's number.
Yeah, 2 times Avogadro's number. And instead of 2 moles, I'm just going to leave this as n moles for now. We know n happens to be 2, but I'm just going to leave it as n for now. And what happens when you multiply Boltzmann's constant times Avogadro's number? Yeah, that's just R, the ideal gas constant. So let's go ahead and combine those. And I think this is going to be a much more useful way of writing the formula for thermal energy. Half the number of modes times nR delta T. Especially because what else does nR delta T equal? nRT could be replaced by, yeah. Yeah, nRT is PV. So typically I would replace nR delta T with delta PV. And I would put the PV in parentheses there in the sense that either or both could be changing. What we care about is the change in pressure times volume. So as before, P final, V final minus P initial, V initial. Although in this case, what's not changing? Yeah, in this case, pressure is not changing. So in this case, pressure can be factored out. And we're left with 1/2 times number of modes times the pressure, which is constant, times the change in volume. So let's try that calculation. 1/2 times number of modes times pressure is 3 during this entire process. 3 times 10 to the 5th pascals, 300,000. And I'll put the times 10 to the 5th pascals outside. And what's the change in volume during this process?
It appears to be 2.
Yeah, we're going from 10 to 12, so plus 2 times 10 to the negative 3 cubic meters. So 3 times 2 would be 6. And as we saw earlier, 10 to the 5th pascals times 10 to the negative 3 cubic meters is just 100 joules. In other words, 600 joules. So it looks like that reduces to delta E thermal equals 1/2 times 6 would be 300 times number of modes. We still don't know the number of modes, but if we can figure out the change in thermal energy, we can solve for number of modes. Any questions on that so far?
Yeah, can you, so I know you factored out P, but why did it just disappear?
The pressure here?
Yeah.
The pressure is 3, and the change in volume is 2. So we're multiplying 3 times 2 to get 6.
Oh, now I see. Okay. You did multiply that.
You got the times 100 joules because of the way the units worked out.
Yes. Okay. Thank you.
Any other questions on that so far? So we at least have, and the N actually gets bundled into the pressure times volume, because nR delta T is equal to delta PV. So the N is included in delta PV. And this is actually one of the really nice things about making that substitution. By writing delta E thermal as half the number of modes times delta PV, we don't need to worry about the ideal gas constant. We don't need to know what the temperature is. We don't even need to know how much of the gas there is. All we need to know is the pressure and volume at the beginning and the end. So that's a very convenient substitution. It only works for gases, of course. For solids and liquids, this wouldn't apply. You'd have to use the nR delta T times half the number of modes formula. But it's a very useful substitution if you're working with a gas. And in general, half times the number of modes times nR delta T works for any substance, no matter what the phase is. So I think this is probably one of the most useful formulas for delta E thermal, if you're dealing with some substance where all you know about it is the number of modes, or where number of modes is what you're trying to find. On the other hand, if it is a known substance, like if you're dealing with, let's say, a certain amount of ice or a certain amount of, I don't know, molten iron or something, if it's a known substance, I would probably just look up the specific heat on the data table. But if it's a more mysterious substance, but you do know or you want to find the number of modes, this is a very convenient formula to use. Any other questions on that so far? So we know that the number of modes times 300 joules is the delta E thermal. Is there any other way we can find the delta E thermal involved here, based on the other information we have about process A? Generally, what causes a delta energy to happen? What's making the energy change?
Is it the change in heat?
Heat is part of it. Delta energy equals heat, and yeah, also work. We can use the first law of thermodynamics here. First law of thermodynamics, also known as conservation of energy, because the delta E thermal, we don't know that yet, other than that it's equal to 300 joules times the unknown number of modes. But we know it's got to be equal to heat plus work. The change in energy has to come from the transfers that happen. We know the heat that's being applied, 2,400 joules. Can we figure out work? Yeah, work is the area under the curve. So let's try that out. Work is the area under this curve, from the curve all the way down to the axis. So that area should tell us the work being done. And how would we find that area?
And just multiply 2 by 3.
Yeah, because we've got width 2, height 3. And you could also think of this as pressure times delta volume as before, or as the usual formula for a constant pressure process. So pressure times delta volume. Pressure is 3, delta volume is 2. And again, we'll also have to multiply by the 10 squared joules to get the units to work out right. So we get 600, because that's 6 times 100, so 600 joules. And during this process, as the gas is expanding, would you say work is entering or leaving? Yeah, work is leaving, so we're going to treat that as what kind of number?
Negative?
Yeah, negative. So this is negative 600 joules of work. And this is actually from the usual formula for work in a constant pressure process is negative pressure times delta volume. And that negative is literally just to take care of that directionality, that if the gas is expanding, you want work to be negative. If the gas is compressing, you want work to be positive. So the negative takes care of that. So we've got heat, we've got work. We can now put those together and say delta U equals heat plus work for a total of how much?
1,000? Oh, wait, it's negative, sorry.
Yeah, because we're essentially subtracting. So yeah, 1,800 joules, positive 1,800 joules. So that's the amount of change in energy. We know the change in energy, which in this case is just E thermal because there's no phase change, equals 1,800 joules. And now we can set that equal to delta E thermal, which is 300 joules times number of modes. And then how do you find number of modes?
Just divide by 300.
Yeah, divide by 300. We get number of modes is 1,800 over 300. Joules cancels out. Looks like that's going to be 6. So I think we can say here that each molecule has 1,800 over 300 equals 6 modes. So 6 modes per molecule. Any questions on that so far?
I have a quick question about that.
Mm-hmm.
So if they tell us the heat involved is 2,400 joules, why is that equal to the internal energy and not the Q for the system?
2,400 joules is the heat, because that's how much heat is being provided. But the change in internal energy is always going to be heat plus work. And in this case, there's heat being transferred. That's the given information. And also work leaving the system, which we calculate as the area under the curve. So the actual, sorry, what was that?
Why is the 1,800 equal to the change in E thermal?
Because that's the combination of the heat and the work. Both the heat and the work are acting to change the energy.
Oh, and there's no bond energy change, so it all goes to E thermal.
Right, exactly. That the heat plus work together tell you the change in internal energy. Internal energy includes thermal energy and bond energy and chemical energy and nuclear energy, but the thermal energy is the only one that's changing here because we know there's no phase changes, there's no chemical reactions going on, there's no nuclear fission or fusion involved. So the only type of energy that's changing is thermal energy, and the processes of heat and work are what's causing it to change.
Okay, thank you.
You're welcome. Any other questions on that one? And looks like there's a couple other questions to deal with. Find the pressure at state 3 and the work in process B. Let me make a note of that and scroll up. C, pressure 3 equals D, work B equals. All right, let's try those. Going back to same graph. So based on what we know, let's take a look at process or pressure 3. So focusing on point 3, we know the volume is 70 times 10 to the negative third cubic meters. we want to know what the pressure is. Let me get this out of the way. So at 0.3, we want to know what is this pressure. I'll just call that P3. And is there anything we do know about 0.3? Do we have any of its values? Yeah, we know its volume. That's 70 times 10 to the negative 3 cubic meters. We don't know its pressure. We do know that it is linked to points 2 and 4 by some processes. Would any of those processes be really useful for getting information about volume or how volume and pressure are related? Because I notice we do know the volume and pressure at 0.2, and we know the volume and pressure at 0.4. Do we know anything about process B or process C that would involve something not changing in a useful way? Process B has no heat. Does that mean there's no change in anything at all? Does no heat mean it's a closed system? Right. No heat doesn't necessarily mean no work. In fact, in this case, we know there is going to be a lot of work, because if you take a look at the idea of work being area under the curve, this curve has a lot of area under it. All this area in here. So that means process B involves no heat, but it does involve lots of work. So that might make process B inconvenient to deal with. There's a lot of work being done, so that means that the change in energy would be difficult to calculate. But yeah, if we take a look at the process from 3 to 4, process C, I think process C is going to be a lot more useful here. Because if we focus on process C, fill that in, process C here, can do better than that. Process C is isothermal. We know there's no change in temperature. If this is isothermal, yeah, we know that there's no change in temp from 3 to 4. So because of the isothermal process, or isothermal curve, we know that temperature 3 is the same as temperature 4. And that's very useful. I think we can make a lot of the use of the fact that temperature 3 equals temperature 4. Because we can use that. How is temperature related to volume, which we know, and pressure, which we're trying to find? Yeah, we've got this direct relationship, right? Specifically the ideal gas law. We can always go back to PV equals nRT. These aren't quite the ideal gas law yet. We just got temperature equals temperature, but we can make that look like the ideal gas law by multiplying by the missing pieces, n times r. So let's just multiply both sides by n times r. And see what we get. Multiplying both sides of the equation by n times r, we get nRT3 equals nRT4. And that means each of those nRTs can be replaced with PV. Specifically, we can say that pressure 3 times volume 3 equals pressure 4 times volume 4. Because nR times T3 equals nR times T4, make the ideal gas law substitution, pressure times volume at location 3 must equal pressure times volume at point 4. Boyle's law. What exactly is Boyle's law? Yeah, if they're at the same temperature, then PV for the first one must equal PV for the second one. That's a direct application of the second law of thermodynamics, or sorry, not the second law, direct application of the ideal gas law. So really just a variant way of stating the same formula. So, and I think we know all of those, right? The only missing piece here is pressure 3. So we can find pressure 3 by doing what? How would you isolate pressure 3 here? Yeah, divide by volume 3, so we get pressure 4 times volume 4 divided by volume 3. And I think it might be useful to look at this by grouping together the volume 4 over volume 3, because we know both of those volumes, 70 and 10 and 70. If you take 10 over 70, and these do both have the times 10 to the negative 3 cubic meters, but those cancel out anyway because it's the same units. So 10 over 70, it just reduces to 1/7. So we're going to, from 3 to 4, we're transitioning to 1/7 as much volume. So we're transitioning to 7 times as much pressure. And that's really the key here. Pressure and volume, assuming constant temperature, pressure and volume are inversely related. We drop the volume to 1/7 of what it was by increasing the pressure to 7 times what it was. So the pressure at 4 is 7 times as much as the pressure at 3. And we can now fill that in. What is the pressure at point 4? Pressure 4 was how much here? Yeah, 2 times 10 to the 5th. So we just multiply that by 1/7, we get 2/7 times 10 to the 5th pascals. So that should be the pressure at location 3, or state 3, 2/7 times 10 to the 5th. So 2/7, so about 28,571. So that would be the pressure at point 3, 28,571, or to write it in consistent units with what the rest of the axis is, 0.28571 times 10 to the 5th pascals. So that's the pressure at point 3. And looking for isothermal curves is very useful in cases like that, because not just at the endpoints, but any locations along this isothermal curve must be at the same temperature as each other, which means pressure times volume is a constant all along that curve. Any changes in one have to be balanced by an opposite change in the other. Any other questions on that part?
Could you just explain again where the 1/7 came from? I got a little confused.
Yeah, specifically looking at, that was from the ratio of pressures. Here. For that one, we just divided both sides by volume 3. So pressure 3 equals pressure 4 times volume 4 divided by volume 3. Grouping the volumes together, that's just a ratio. Volume 4 over volume 3, that's volume 4, which is 10, over volume 3, which is 70. 10 over 70 reduces to 1/7.
Yes. Okay. I see now. Thank you.
You're welcome. Any other questions on that? All right, and then part D, we're looking for the work done during process B. So that's what we briefly looked at this earlier with the area under the curve. Let me fill in pressure 3 now that we know that. That's 0.28. Let's round that off to 0.286. So we're now actually looking for that mysterious work done. In other words, the area enclosed under process B. So we want to know this area here. I guess I should make that a little more fitting inside the curve. We want to know this area. We want to know the work done during process B. And finding the area under the curve is going to be really inconvenient because that's not a nice, neat shape. We could approximate it using a triangle and a rectangle, but that wouldn't be a very good approximation because this is a curve. But we can find the work in other ways, probably by going back to the first law of thermodynamics, conservation of energy. We can say for certain that delta U equals work plus heat. And what do we know specially about process B? What's the important information we have about that process? Yeah, work is 0. This is an adiabatic process. There's no heat, which means any change in internal energy must come from what instead? Yeah, work and work alone. The change in energy is the work done. So that means when part D is asking what's the work done during this adiabatic process, it's really just asking what's the change in internal energy. So we can use any formula we want for delta E thermal, since the change in energy is just thermal energy here. And we know the pressure and volume before. And now that we've done the calculation in part C, we know the pressure and volume after. So I think we can probably just use the formulas we've already been using for delta E thermal, specifically 1/2 times number of modes times delta pressure volume. So let's try that. 1/2 times, and how many modes do we have for this particle? Yeah, 6 modes based on the work we did earlier. And then times delta pressure volume. In this case, pressure and volume are both changing, so we can't pull anything out of the delta. We're just going to have to write it as pressure final, V final, volume final, minus pressure initial, volume initial. But I think we now have all those values. 1/2 times 6 is just 3. P final, V final, that would be at 0.3, so 70 times 0.286. Minus P initial, V initial, that would be 3 times 12. And of course, that whole thing also needs a times 10 to the second joules because we're multiplying 10 to the 5th pascals times 10 to the -3 cubic meters. So I think that should be our calculation. 1/2 times the number of modes is 3. Pressure final times volume final would be 70 times 0.286. Pressure initial times volume initial would be 3 times 12. And we also have a times 100 joules to get the units to work out right. Any questions on that setup so far? So we multiply that out. 3 times 70 times 0.286 minus 3 times 12 will be 36 times 100. I'm getting negative 4,794 in joules. And since there's no heat, all of that delta E thermal is going to be work. So during this process, we should expect work to be removed from the system to the tune of 4,794 joules of it. And the negative corresponds to what's happening to the volume during this process. During process B, what happens to volume? Yeah, volume is increasing, the gas is expanding. Does that match up with the expectation that work is leaving the system? Yeah, if the gas is expanding, presumably it's pushing outwards on the piston. So the gas is doing work to the piston, work is leaving the system, which matches up with the negative value we get here. So that should be the amount of work that leaves the gas during that process B, the adiabatic process. Any other questions on that one?
So I understood the equations and everything, but how did you know from the graph that process B, the Q was 0?
We can't really tell from the graph. The adiabatic process does form a certain type of shape, but it's really difficult to recognize visually. But this one did actually specify that process B is adiabatic.
Oh, I see. Okay.
So that's really the key to the whole thing, that it gives us that information.
Okay, thank you.
Mm-hmm. And in situations like this, I would specifically look for information like that. And like as soon as you know what you're trying to find, and I would recommend doing that first. Skim through the problem, figure out what is it actually asking for, but then go back and look for useful pieces of information like that. If it specifically tells you information about one specific process, what's going on in that process, make note of that, even just write it down off to the side as a reminder. And it's often a good idea to just make a chart of the information you know, like just list out process A, process B, process C, process D, just list out everything you know about each process that might be useful. Like this process has constant pressure, or this process involves no heat being applied, or this process is constant temperature. List out what you know so you can refer back to that later. Any other questions on that? All right, then let me pull up another example. Let's see what else we can do here. Let's try this one with the bond energy, because we haven't done that in a while. I think that'd be good for review. This one here. So here we got a cluster of just 5 molecules, and we want to know the exact bond energy. And we can find the exact value here because with a small cluster, it's actually possible to list out all the possible bonds. And so to do that, let me make some more room here. If we just, let me actually label these first. Let's just call these molecules, it's useful to be able to refer to them. Let's say molecule A, molecule B, molecule C, molecule D, molecule E. Just so we have a reference for naming them. Then what sort of bonds would we want to include in our calculation if we want to list all the possible bonds? Like what would be some examples of bonds we would want to include? Like bonds from where to where? I mean, just in the sense of what would be examples of particles that are bonded together here? If we try the nearest neighbors, for instance, like A is bonded to which nearest neighbors? Yeah, we've got A to B, B to D. What are some other nearest neighbor pairs? If we just list out all of them, what would the other ones be? B to C, B to D, B to E, and C to E. I think that's, do we have any more? Yeah, D to E as well. Those are nearest neighbors. And I think that's all of them because it looks like none of the other ones have any other neighbors to be bonded to. For instance, A has only these 2 nearest neighbors. B is nearest to all 4 of the others. D has 3 nearest neighbors, so does E, and then C has 2. So that means that we have listed out all of the nearest neighbors. So 5 nearest neighbor bonds. And what would be the energy of each one of those nearest neighbor bonds? What do we typically call the bond energy of one single pair of nearest neighbors? Yeah, that's just -1 epsilon. So that's negative epsilon each. Multiply those together. Each one of them has negative epsilon times 5 of them. So -5 epsilon would be the energy of all 5 of those bonds. Of course, those aren't the only bonds because what other bonds do we need to consider? If we really want all of them. Yeah, let's take a look at the next nearest neighbors, the second nearest neighbors. So for instance, A is very close to B. What's a little bit further away from A? C. Specifically, C is how far from A? How would you describe that distance? Yeah, 2 times R naught. And typically we would take that 2 times R naught and look that up on a graph, the Leonard-Jones potential energy graph, but it actually just gives us that value here. If the distance is 2 times R naught, then the energy is -0.015 epsilon. So we have one bond of distance 2 R naught. Are there any other bonds of that distance?
Maybe like A to D? Oh, wait. No, sorry. I got confused. Never mind.
C to D. Is C to D the same distance?
It doesn't look exactly like linear.
Yeah, that looks like a little bit closer. In fact, you can often tell more easily by drawing out circles. If you draw out a circle centered at, let's say, centered at location at C. If you imagine that circle expanding evenly in all directions, and it's difficult to draw this in this interface, but if you imagine this circle expanding outwards in all directions, the first atoms it hits are B and E. So B and E are both the same distance from C, and those would be the nearest neighbors. If you expand it a little further, what's the very next molecule it's going to hit? Yeah, that expanding circle of distances hits the center of D, and we should really be treating the centers as the location we care about. Hits the center of D a little bit before it hits the center of A. So that means D is actually closer to C than A is to C. Which means this red line, the distance 2 R naught, is actually a third nearest neighbor. So we'll definitely want to consider that, but we'll consider that later. Let's start with the second nearest neighbors. So that will be, why are there only 5 nearest neighbors? Wait, oh wait, that's right. There's a lot more than 5, right? 1, 2, 3, 4, 5, 6, 7. Because we're not counting number of particles, we're counting number of bonds, and it looks like there are 7 of those. So yes, that should be -7 epsilon. So yeah, that's an important thing to keep in mind. Don't count the number of particles, count the number of bonds. 7 bonds means 7 times negative epsilon. Thank you for noticing that. Otherwise, we would have gotten way off from the actual answer. And let me put this second nearest neighbor aside for now. We'll come back to that later. But let's take this third nearest neighbor. But for the second nearest neighbors, that would be for example, from C to D. Are there any others that are that length?
A to E?
Yeah, C to D and A to E. And I think that's it, because the only other bond we haven't counted would be from A to C, and that's a little bit longer. So it looks like there's only 2 nearest bonds, or the second nearest bonds. So there's 2 copies of the second nearest bond. And to figure out the energy involved there, we're going to need a distance. So let me put this aside for now, and let's take a look at...
oh, sorry.
Sorry, what was that?
Nothing. I thought I was muted.
Oh, okay. So we don't know the distance from A to E, but we do know the distances from particle to an adjacent particle. So let me draw out some of those a little larger. We know all these blue distances are R0. But what we actually want to find is this longer distance. So if we label those, we've got R0. Those are all just R0. Do you see any way we could figure out what this longer distance is based on these 2 triangles? Any methods from geometry that look like they'd be useful there? Yeah, we could probably use the Pythagorean theorem. We just need to set up a right triangle first, because Pythagorean theorem specifically applies only to right triangles. So let's see if we can find a right triangle here. Let me expand this a little bit. And I haven't really drawn this exactly to scale. The important thing is that all of these blue lines should be considered the same length. Do you see any right triangles in this? Or any right angles at all? These blue triangles should be equilateral, right? So we've got complete symmetry. If this is completely symmetric, then the green line should be bisecting the blue line and splitting the angles exactly in half. Yeah, that's a right angle right there. Because the green line is splitting the blue line exactly in half. So it's crossing those at right angles. And we can just focus on any one of those. Let's say this one. There's a right triangle. Do we know any of the side lengths in that right triangle? For instance, we know this side is R0, right? What about this shorter leg here? What would that have to be? Remember, this was originally an equilateral triangle. We've got, for instance, distance from C to D was exactly R naught. We just cut that exactly in half. So what's left? Yeah, that's R naught over 2. And now we've got two sides. And the missing side, we just call that distance x for now. Actually, the whole thing is x. Let's say we call this entire distance, the second nearest bond, x. Then this distance would just be x over 2. So our right triangle here has side lengths x over 2, r naught over 2, and a hypotenuse r naught. And we can write the Pythagorean theorem for that. We've got leg squared plus leg squared equals hypotenuse squared. And multiply that out, x squared over 2, or x over 2 squared becomes x squared over 4. R naught over 2 squared becomes R naught squared over 4. And then R naught squared is just R naught squared. And then how would we isolate x here? Algebraically, how could you get x by itself in this equation?
Can't you just subtract the r naught squared to the other side and then just take the square root?
Sounds good. X squared over 4 equals R naught squared minus R naught squared over 4. And then, yeah, we'd want to multiply by 4 first. So multiply both sides by 4. We get x squared equals, and we're distributing the 4 to both of these. So 4 R naught squared minus 4 times R naught squared over 4. The 4's cancel out, so just R naught squared. And then we can combine those like terms to get how much? Yeah, that'll just be 3 R naught squared because we got 4 of them minus 1 more. And at that point, we can take the square root of 3 R naught squared. And we can split up the square root into square root of the first thing times square root of the second thing. Square root of 3 is just square root of 3. Square root of R naught squared becomes R naught. So that distance, the total distance of the green line there, that second nearest neighbor bond, as distance square root of 3 times R naught. So we now know that second nearest neighbor distance. Any questions on that so far? And now that we know the distance, how do we convert that into energy? Where can we find the energy of a bond with that thing? Do we have that in the chart somewhere? Yeah, square root of 3 as the distance, square root of 3 R naught, corresponds to an energy of negative 0.036 epsilon. So that would be the energy associated with this. We've got 2 second nearest neighbor bonds at negative 0.036 epsilon each. So multiply that out, and that should tell us the energy of both of those bonds together. Two times negative 0.036 would be negative 0.072. So that would be the energy of both of those second nearest neighbor bonds together. Any questions on that so far? And are there any bonds that we still need to consider?
The third nearest neighbor?
Yeah, and it looks like we only have one of those, right? From A to C. Because there are no other bonds that are that long in the system. So for the third nearest neighbor bonds, distance is 2 times R naught, because we just got A to B and B to C, 2 copies of R naught. And so we should be able to use this line from the chart. 2 times R naught as a distance gives us negative 0.015 epsilon as the energy. So we have one third nearest neighbor bond at negative 0.015 epsilon each. So that's just negative 0.015 epsilon. And let me get these geometries out of the way. So I think we now can just combine those. We have the bond energy from all of the bonds, the 7 nearest neighbor bonds, the 2 second nearest neighbor bonds, the 1 third nearest neighbor bond. That should be all the possible combinations, all the possible pairs. So we can just add those up. E bond equals negative 7 epsilon plus negative 0.072 epsilon plus negative 0.015 epsilon for a total of 7.087 epsilon. So that would be the bond energy here. Any questions on that? And by the way, there's also a useful technique to make sure to figure out how many bonds you can expect in total if you want to make sure you really have all of them. If you take a look at this whole cluster, we have how many molecules here? In total, counting everything, we've got how many molecules? Can you count them? We've got a diagram, right? We got 1, 2, 3, 4, 5 molecules. Each one of those molecules we should expect to be interacting with how many other molecules? Yeah, each one of those interacts with 4 others. A is interacting with B, C, D, and E. B is interacting with A, D, E, and C. C is acting with E, B, D, and A, etc. So we should expect 4 bonds per molecule. And this sort of situation is often referred to as a handshake problem. If you imagine you've got 5 people and each one wants to shake hands with everybody else, so each person has 4 handshakes available, we can just multiply those. If you multiply 5 people times 4 handshakes per person, what would you get? Yeah, we should expect 20 handshakes or 20 bonds. Did we count 20 bonds here? No, how many did we get? 7 plus 2 more plus 1 more. Yeah, we got 10 bonds. But if we're saying each molecule has 4 bonds, we're saying A is bonded to B and C and D and E, and we're saying B is bonded to A and C and D and E. We just counted the bond from A to B, and we also counted the bond from B to A. Are those different bonds or the same bond?
They're the same.
So if we're counting the same bond twice, then 20 bonds is too big. What do we need to do to get back down to the actual value?
Would you just divide by the 2?
Yeah, divide that by 2 to get 10 bonds. Because if we're saying every molecule has 4 bonds, then we're counting each bond twice. So we divide by 2 and there's actually 10 bonds. And this is the same idea with the handshake problem. If person A shakes hands with person B and person B shakes hands with person A, that's really just one handshake. That doesn't really count as different handshakes. So 5 people can shake hands 10 different ways. 5 molecules have 10 bonds between them. And which one of those are nearest neighbors or second nearest neighbors or third nearest neighbors depends on the layout. But no matter what the shape is, if you have 5 molecules, there's a total of 10 bonds. And if you look at the ones we've got, 7 plus 2 more plus 1 more, that's 10 bonds. So we know we have truly all of them. And note that we didn't use 10 bonds in any of our calculations, but it's often a useful thing to do if you want to make absolutely sure that you really have all the possible bonds. That if you calculate using this sort of handshake approach, number of molecules times number of bonds per molecule, which should be 1 less than the number of molecules, divided by 2 to eliminate double counting, that tells you the total number of bonds of any type. And then once you list out the bonds, if you're looking for all the bonds, total those up. 7 plus 2 more plus 1 more is 10. So at that point, we can be certain that we really do have all of them. There is no more hidden bonds that we missed. So this can be a useful combinatoric approach to make sure you really have all of them. Any other questions on that? Or any other questions on the bond energy stuff in general?
Are you going to go through part B as well?
Oh, was there a part B to this?
Well,
let me see if I've got that. What was part B asking about?
I think it's one of those cases where you have to, oh, hold on, just give me 1 moment.
Oh yeah, this was same idea, but you've got 3 moles of it.
Mm-hmm.
Yeah, let's try that as well. And we want to know E bond for that solid. Yeah, let's try that out. Let me pull that up as a different document actually. There it is. Clear off the solutions to make some more room. Okay, so in this case, we have not just a few molecules, we have this enormous cluster of molecules, 3 times Avogadro's number of them. So like 1800 hextillion. But we're assuming it's 2-dimensional, so it's just this vast hexagonal grid spreading out over a 2-dimensional plane. And we want to find not the exact bond energy, we just want to find the contributions from the nearest neighbor and second nearest neighbor bonds, because otherwise it would be way too complicated. We don't want to try figuring out all the bonds, especially since, what did you notice about the contributions from like the third nearest neighbor bonds in the previous problem? How much energy was contributed by the third nearest neighbor bonds, for instance, compared to the nearest and second nearest?
It was very little compared to the others.
Right. Very, very little energy. So when you get to third nearest neighbors and beyond, it's a very small amount of energy. If you look at just the nearest neighbors and that's it, you get a pretty good estimate. If you look at the nearest neighbors and second nearest neighbors together, that gives you an even better estimate. But beyond that, it's kind of turns into a waste of time. You're spending a lot of extra time to get very little more accuracy. So in this one, we're focusing on just nearest and second nearest. But we're looking at lots and lots of particles. So let's try this approach again. If we have the nearest neighbors, each one is going to be negative epsilon each. But instead of just having like 7 of them, we're going to have huge amounts of nearest neighbors. If we take a look at one single typical atom, let's say we're focusing on, let's say, this one. How many nearest neighbors does that one atom have? How many other atoms are directly adjacent to it? Yeah, it looks like 6. Because this is a hexagonal arrangement. We've got this one, this one, this one, and so on. So we've got 6 nearest neighbors per atom. And to figure out the total number of bonds of that type, how many atoms are we dealing with? In this entire enormous cluster, how many atoms do we have? Did this problem tell us how much there is? Didn't it? I thought it said, starts by saying 3 moles of solid argon, right? 3 moles is how many molecules? How many atoms? Or how many atoms are in 1 mole? What do we call that amount? What does 1 mole mean? Yeah, that's Avogadro's number. So 3 moles would be 3 times Avogadro's number. So we've got 3 times Avogadro's number atoms times, and we already saw that each one of those atoms has 6 bonds. 6 bonds per atom. So if we just multiply 3 times Avogadro's number times 6, would that give us the number of bonds? Or do we need to make any other modifications there? Like if we say, for instance, this atom has 6 nearest neighbors, can we also say, for example, that this atom also has 6 nearest neighbors? If we try that out, we've got 1, 2, 3, 4, 5, 6. Is that going to lead to any problems?
Wouldn't you divide by the 2 because you're doing the double counting again?
Yeah, it looks like this definitely double counts. This green atom has 6 nearest neighbors. This red atom has 6 nearest neighbors, one of which is the green atom. So that bond already got counted. If we say every atom has 6 nearest neighbors, which is true, but we're double counting. So we do need to divide that by 2. So 3 times Avogadro's number times 6 bonds per atom divided by 2 to eliminate double counting. That'll be 3 times 6 divided by 2 would be 9 times Avogadro's number. So there's 9 Avogadro's number bonds of this type. at negative epsilon each. So we end up with 9 Avogadro's number times negative epsilon would be negative 9 Avogadro's number epsilon. So that would be the bond energy contribution from just the nearest neighbors. And that alone is going to be a pretty good estimate. But we can get a better estimate by looking at the second nearest neighbors as well. Any questions on that contribution so far? So let's take a look at the second nearest neighbors, see if we can make any sense of that. What would be an example of a second nearest neighbor if we go back to what we were looking at from the previous one? If we were looking at, let me clear this out. Let's say we're still talking about some central atom. And we want to find its second nearest neighbors. Again, you could imagine this gradually expanding circle or sphere. So we've got this circle that's gradually expanding outwards in all directions. The first other atoms it hits are these 6. So those are the nearest neighbors. As it continues to expand outwards, there are a few other atoms it's going to hit. And notice that it hits the center of this one before it hits the center of this one. So this one's a little closer. So drawing that out, we've got this one is a second nearest neighbor. So is this one, but not this one off to the side, because that's a little bit further. It goes beyond that circle to get to the center. But we've also got, looks like this one hits the center, and this one hits the center at the same time. So it looks like these 4 count as second nearest neighbors. Are there any others not shown on this diagram that are that same distance? Yeah, one on top and one on the bottom. So straight up. And notice that to get to the second nearest neighbors, we're basically shooting straight through the middle of 2 nearest neighbors. We should expect one up here and one down here. Even though they're not explicitly shown on the diagram, the ... means this keeps going. We should expect that this means there's more atoms up here and more atoms down below as well. They're just, even if they're not shown on the diagram directly. So it looks like we actually have 6 second nearest neighbors. We've got this one, this one, this one, this one directly below, this one off to the side. So those would be the 6 nearest neighbors, 6 second nearest neighbors. So to make those calculations, we could say the second nearest neighbors, we still have 3 times Avogadro's number atoms. Each one of those atoms, it looks like, has 6 bonds of this type per atom. And do we need to divide by 2 to eliminate double counting here? For instance, if we try focusing on all the nearest neighbors of this atom, we could say that has nearest neighbors above, make that thicker, above, up and to the right, down and to the left, below, down to the left, up into, yeah, it looks like we are double counting, right? We just counted that bond twice. So if we do this, say each one has 6 second nearest neighbor bonds per particle, then we are going to count every bond in the whole system twice. So we do need to divide this by 2. And I find it's often useful to look at it in that sort of way. If you're not sure whether you're double counting or not, try just actually drawing out the however many bonds for each particle in some small region. If you mark one of the bonds twice, that means, yes, you are double counting. So it looks like that's, again, 3 Avogadro's number times 6 divided by 2 is 9 Avogadro's number bonds of this type. And what's the energy of one of those second nearest bonds? Did we have that value from earlier? If we go back to this one, second nearest neighbor bonds was this one, right? Square root of 3 is the distance, negative 0.036 epsilon. So we can still use that. It's still the same bond we were looking at earlier. We're just looking at lots more of them now. So we can still call that negative 0.036 epsilon each. So then we just multiply those. 9 times negative 0.036 epsilon is 0.324. So negative 0.324 Avogadro's number epsilon. So that would be the bond energy contribution of all of the second nearest neighbor bonds. And then to get the actual bond energy, we can just add those together. Negative 9 times Avogadro's number times epsilon plus negative 0.324 times Avogadro's number times epsilon is negative 9.324 Avogadro's number epsilon. And then you could actually fill in Avogadro's number, 6 times 10 to the 23rd. And I think it gave us a value for epsilon somewhere. Yeah, 120 times 10 to the negative 21 joules. So fill those in, multiply, and you get the bond energy in joules. Any other questions on that one?
Could you explain again the double counting? I got a little confused.
Yeah, if you're not sure whether you're double counting or not, I would recommend, let me clear this out so we can take a closer look. If you're not sure whether you're double counting, what I would typically do is try drawing out some of the bonds. Like if we are claiming that there's 6 second nearest bonds per atom, let's take a look at, let's say we focus on this atom. Mm-hmm. We're saying this atom has 6 second nearest neighbor bonds. If we draw those out, that's this one, this one, this one, this one below, and the one over here. So 6 bonds. But if we take a look at other atoms nearby, in particular, let's say we focus on this one. We want to say this atom also has 6 second nearest neighbor bonds. And if we actually mark those, we've got this one over to the right and below, directly below, to the left and below, and to the left and above. And the critical idea here is that we have just marked a bond twice. Specifically, this bond, we have just marked twice. Mm-hmm. Which means this approach, multiplying number of atoms times number of bonds of this type per atom, that approach is double counting. It's counting this bond from, let's say we call these A and B. We just counted the bond from A to B and the bond from B to A. Those are not really different bonds though, so just multiplying gets us twice as many bonds as we should actually have. So we need to divide by 2 to balance that out.
So anytime we're drawing bonds and they overlap, just divide by 2?
Yeah, if you've specifically drawn the same bond twice.
Okay. Got it.
Any other questions on that? All right, let's take a look at another type of problem then that I think is going to be useful for bringing together some ideas. I wouldn't necessarily always assume there's double counting because it kind of depends on how you're tallying them up. And in some cases, maybe it's not double counting. Another one I wanted to get to, at least get a start on, is this one with the graph of temperature versus energy. Because I've been seeing a lot of people ask about this in the Discord. That we have some mysterious new substance. We've got a whole bunch of values about it. We know how many atoms there are. We know the bond energy when it's a solid. We know the melting point, the boiling point, heat of vaporization, heat of melting. And we want to figure out, we want to draw the temperature versus energy graph. So let's start by just listing out everything we know about this substance. We know there's 50 atoms in the substance. We know the E bond for the solid is negative 350 times 10 to the negative 21 joules. We know the melting point is 75 Kelvin. We know the boiling point is 125 Kelvin. We know delta H melt is 50 times 10 to the negative 21 joules. We know delta H boil is 250 times 10 to the negative 21 joules. We also know it's monoatomic in solid or liquid, but when it vaporizes, it forms a diatomic gas with no vibrational modes. So it looks like that's everything we know about this substance. And we want to make a graph of energy versus temperature. Any questions on that so far? So for a moment, think way back to the very beginning of the quarter. When was the first time you saw a graph of temperature versus energy? What sort of graph were we looking at way back at the beginning? Yeah, the three-phase diagram. We are essentially creating a three-phase diagram for this new substance, but we're going to need to fill in the values ourselves. So to do that, I mean, we should expect this to look like the three-phase diagram. Presumably this is going to be, and this is just a rough sketch here. We should assume some sort of increase in temperature as you add energy, and then we get to a melting point. We're going to add energy but not change the temperature. Then when it's finished melting, we add energy to change the temperature. Then we get to the boiling point, add energy to change the phase without changing the temperature, and then add energy to heat up the gas. So we should expect the graph to look something like this. We're just going to want it more accurate than that. To begin with, we're going to need a starting point. We don't know maybe how high or how low this graph should be. Any idea how we could choose what value to start at when we're at the very beginning of the graph? Like at the very beginning, what's the temperature at that very beginning on the far left side of the graph?
Can we assume it starts at 0 or?
Yeah, I mean, it looks like that based on the graph. This is a graph in temperature in Kelvin. If you count backwards, you got 100, 75, 50, 25, 0. And also it looks like each tick mark represents 5 kelvins, I think. So the beginning is temperature 0. And this is in some ways a lot like finding the y-intercept of a graph way back in beginning algebra. You want to find the y-intercept, you set the input equal to 0. So we're trying to find the energy intercept by setting the temperature equal to 0. If temperature is 0, how much thermal energy do we have? What would be the thermal energy if our temperature is all the way down at absolute zero? If it's the coldest you can possibly get, how much thermal energy is that? Yeah, 0 joules. Because remember, thermal energy can be thought of as, well, one way to write it would be MCT. If temperature is truly 0 kelvins, then there's no thermal energy at all. Which means the only energy we have is what? What's the only type of energy this would have at absolute 0? Yeah, E bond. And it tells us the bond energy of the solid phase. In solid form, the bond energy is -350 times 10 to the -21 joules. So we can use that as E total. When the temperature is 0, the total energy is just the bond energy, which we know is -350 times 10 to the -21. So that will be the starting point for our graph. And let me zoom in on this a little more so we can get more detail. We know we want to have -350 times 10 to the -21 as the starting point. So let me mark that on the graph. -350. That'll be down here. So that's a point we can use on the graph as a starting point. And then let's say we add some energy. If you've got this substance that's at absolute 0 and you add energy to it, what would you expect to happen? You add energy, and what else happens? What type of energy would you expect we'd be changing here? Yeah, thermal energy, which means you're going to be raising the temperature. This is where we get this diagonal line. Up and to the right means you're adding energy to raise the temperature. But that's only going to go as far as what temperature? What's the hottest this can get before something else happens?
75?
Yeah, 75. Because as soon as it gets to 75, what's going to happen?
It melts.
Right. So let me put in some boundary lines there. We know that at 75 and also at 125, we get phase changes. So let me put some marks there so we don't accidentally cross those. We've got something happening at t equals 75. Make that a little narrower. We've got phase changes at 75 and also at 125. So we can essentially split this up into the solid phase and the liquid phase and the gas phase. This entire interval is solid. And then this entire interval would be liquid. And then after that, this entire interval would be gas. So by splitting that up, we can focus on just one at a time. For instance, if we're in the solid phase, can you figure out what the slope, we know it's going to be a line of some sort. We know it's going to be a diagonal line up to 75. But is there any way you could figure out the slope of that line, how high it actually gets before it hits 75? Can you predict how much energy it would take to get it from 0 kelvins to 75 kelvins? Delta H melt, that's specifically talking about what sort of process though? Is this substance in the process of melting right now?
It's, yes.
It's eventually going to melt. Once it reaches 75, if we add more energy, then it's going to melt. So delta H then. But yeah, for this period of time, thermal energy is what matters here. If all we're doing is adding energy to raise the temperature, that's a change in thermal energy. And how would we calculate how much the thermal energy is changing? Do you have any formulas for change in thermal energy we could use here? If we know, like we don't know what substance this is, but we know it's monoatomic, and we know there's 50 atoms. What could we use for thermal energy based on number of atoms and what type of atoms they are?
Well, we have the number of modes.
Yeah, this is monoatomic.
So 1/2 number of modes, KB delta T.
Yeah, 1/2 times number of modes times, and NC delta T would be useful if we knew what type of substance this was, so we could find C, and also if we knew how many moles. In this case, 50 atoms is much, much less than 1 mole, so I'm not sure if that would be very useful in this case. But we do know that the energy, the change in thermal energy is 1/2 times number of modes times Boltzmann's constant times delta temperature times the number of particles. Because each individual molecule or each atom should have 1/2 kBt times number of modes. Because remember, 1/2 kBt is the energy of one mode multiplied by number of modes per particle, and that gives you the energy per particle times number of particles, and we get the energy of the whole substance. So this is really just taking, 1/2 kBt as the energy per mode times number of modes, that scales it up to 1 atom, times number of atoms, that scales it up to the whole thing. And then we also put in a delta because what we care about is the change in energy. And in this case, how many modes are we dealing with? If it's a monoatomic solid, how many modes would each particle have?
6, was it?
Yeah, should be 6, because we've got 3 kinetic energy modes. The molecule is able, or the atom is able to vibrate in three dimensions, and also 3 potential energy modes. It's able to interact with its neighbors in 3 dimensions, to the sides, in front and behind, and above and below. So 1/2 times 6 modes per particle times Boltzmann's constant times change in temperature. Let's say we're talking about the full 75 kelvins. Times number of atoms would be 50 atoms. So 1/2 times 6 would be 3, times 50 would be 150, times 75 would be 11,250. And what's Boltzmann's constant? Anyone happen to have a value for Boltzmann's constant handy? Let's see if I can find that in here. Every gigantic physics textbook should have a list of constants at the back. Boltzmann's constant, 1.38 times 10 to the negative 23rd. So 1.38 times 10 to the negative 23rd joules per Kelvin. Let's see what we get there. 11,250 times 1.38 is 15,525 times 10 to the negative 23rd joules per Kelvin. However, this axis is in units of 10 to the negative 21. So I'm going to split that out. 10 to the negative 23rd is the same as 10 to the negative 21 times 10 to the negative 2, because those add up to negative 23. If I combine the 10 to the negative 2 over here, that's just going to shift the decimal point. So 15525, shift the decimal point over 2 spaces, times 10 to the negative 21. So 155 times 10 to the negative 21 joules per Kelvin Oh, and the kelvins cancel out also. Forgot about that because I've got kelvins in the temperature. So we can just go up 155 from the original negative 350 in terms of energy. So we start at negative 350, we go up 155, negative 350 plus 155 would be 150, so negative 145. So 145 is going to be something like that. And let me label the data here. At this point, the temperature is 75 Kelvin and the energy is that can't be right. Negative 350 plus 155, negative 195. So that should actually be more like this. So that is our graph so far. For just the solid phase, we're increasing temperature by 75 and increasing energy by 155 joules. Well, 155 times 10 to the negative 21 joules. So that would be the boost in energy. We're going up 155 from negative 350 up to negative 195. Any questions on that so far? And then from there, what's the next thing that happens if we add more energy? The 10 to the, which 10 to the 2? Oh, the 10 to the negative 2 here. That was just from splitting up the 10 to the negative 23. Because I got an answer in terms of 10 to the negative 23 from Boltzmann's constant. But I noticed that the axis here is labeled in units of 10 to the negative 21. So I think it would be useful to just write everything in terms of something times 10 to the negative 21 joules. And 10 to the negative 23 is the same as 10 to the negative 2 times 10 to the negative 21. Because you can split up exponents as multiplication. So the 10 to the negative 2, I combined with the 15,000 to get 155, just by moving the decimal point. And then the 10 to the negative 21 joules I'm keeping, because that's the appropriate units for this axis. The important thing is we want to be able to have everything written in the same units. So I'm just thinking of 10 to the negative 21 joules as the units of measurement. At this point, though, we've now reached 75 Kelvin and we keep adding energy. It can't keep getting hotter yet, though, because what has to happen first? Yeah, it goes through this phase change, it melts. And how much energy does it take to melt this? What information do we know about the melting process here?
50 times 10 to the negative 1 joules.
Yeah, that is the energy it takes to melt. And usually if that had been listed as like some number of joules per mole or joules per atom or something, we need to multiply by number of moles or number of atoms to get the number of joules to melt that sample. But since it's just listed as joules, I would interpret this as this is the energy it takes to melt this sample. So I would just treat that as the energy you'd have to add to melt the whole thing. So we just take what we're at now, negative 195, and add 50, because the 10 to the negative 21 joules is already the correct units. So we add 50, negative 195, plus an extra 50 would get us up to negative 145. So our new state is now still 75 Kelvin, but now liquid. I should probably specify that in the other one as well. That was 75 kelvins in solid form. We're now at 75 kelvins in liquid form with an energy of negative 145, because we've added an extra 50 to change it to liquid. So let's mark that on the graph. Negative 145 is going to be about here. something like that. And so that's our entire melting process, just this little jump from negative 195 up to negative 145. That's the melting process. And then what's the next thing that happens? We finish melting it, we keep adding more energy, and what happens there?
Now it starts to go, now there's like the change in E thermal, and it starts to go towards the boiling point.
Yeah, exactly. We're going to get another thermal energy change as it warms up. We add energy and increase the temperature approaching 125. So let's take a look at that entire interval all at once. From 75 to 125, what's the change in temperature there?
It's at 75 right now?
Yeah, from 75 to 125.
Oh, it's 50.
Yeah. So the temperature is plus 50 Kelvin. And we can use the same formula. The liquid still has 6 moles per particle. So delta E thermal is going to be 1/2 times 6 times Boltzmann's constant times 50 Kelvin times, and we still have 50 atoms. Which means we could run through the calculations again, but as a shortcut, 50 Kelvin is 2/3 of 75. So we should expect 2/3 of the energy. 155 times 2/3 should be 103. So that means during this 50 Kelvin process, we should expect to be raising the energy by about 103 joules. Or 103 times 10 to the negative 21 joules. So we are at negative 145. We increase by 103. Negative 145 plus 103 would be negative 42. So our next stopping point would be temperature equals 125 in liquid form, and energy equals negative 42 times 10 to the negative 21 joules. Make that a different color. That's going to be difficult to see. So we now reach negative 42. It's going to be something like this. And there's our transition. And note that that has the same slope as before. We haven't really changed any of the properties that are important for delta E thermal. So it still has the same heat capacity and therefore the same slope. We've now reached 125. And what's the next thing that happens?
Another increase in just bond energy.
Yeah, which means it's going to just jump straight up again because we're vaporizing it, but not changing the temperature.
Mm-hmm.
So we're going to go straight up, and specifically straight up by how much?
250.
Right, because that's the delta H for boiling. So we're at negative 42. We add 250. That should put us at 208. So our next situation is temperature equals still 125, but now in gas form, vapor. Energy is negative 42 plus 250 would be 208 times 10 to the negative 21 joules. So that would be 208, something like this. And know that that's a very big jump. Going from solid to liquid means you're breaking some of the bonds, allowing more freedom of movement. But going from liquid to gas means you're breaking all the rest of the bonds. Well, not all the rest of the bonds, because this doesn't turn into a monoatomic gas. What does this turn into?
Did it say it was a diatomic gas?
Yeah, this one turns into a diatomic gas. So we're breaking almost all the bonds, but we're still leaving individual pairs bonded together as chemical bonds. Which means instead of having a monoatomic solid or monoatomic liquid, we now have a diatomic gas. That's a different number of moles per particle, so that's going to change the slope. We can still use our usual delta E thermal formula. Let's say we're going from 125 to We could go from 125 to anywhere because there's no other stopping point really. There's no other going from gas to something else. But let's say from 125 to, let's just go to 175 to finish off the graph. So we're still adding 50 Kelvin. But we need to make some modifications. If this is a diatomic gas, how many modes does it have per molecule?
Without the vibrational modes, I think it's 5.
Right, because we've got the 3 translational modes and 2 rotational modes. The particle can move, or the molecule can move around in 3 dimensions, and it can rotate around 2 different axes. Its own axis of symmetry doesn't count. And no vibrational modes, so just 5. Also, instead of 50 atoms, if these are diatomic, you've got 50 atoms, they merge together into diatomic molecules. How many diatomic molecules do we now have? If you got 50 atoms and you form them into pairs, how many pairs are there? Yeah, we have 25 diatomic molecules. So even though it was 50 atoms, those 50 atoms in diatomic form are now acting as 25 particles. So we multiply all that together, 1/2 times 5 modes per particle times Boltzmann's constant times 50 kelvins worth of temperature change, if we're talking about that 50 Kelvin interval, times 25 molecules, and I'm getting 43 times 10 to the negative 21st. Yeah, 43 times 10 to the negative 21st joules. So that means during this process, the next 50 Kelvin worth of increase, and it didn't have to be 50, that's just a convenient number on the graph, we get an increase of plus 43. So the final state at the far right side of the graph is going to be temperature is 175 in gas format. Energy is 208 plus another 43 would be 251 joules times 10 to the negative 21st. So marking that on the graph, 251. And now we can finish this off with that last diagonal. And note that that is a different slope from solid and liquid because we have changed the number of modes and also even the number of particles effectively. But this would be the complete graph there. Any other questions on that? All right, we are out of time, but I think we managed to cover a good large number of topics. So keep working on those practice finals and feel free to email me if you have any other questions. Good luck on finals, and I will see you later.
Really fast, that last slide, would you post that in the Discord with the graph and stuff?
Yeah, sure. I'm going to post the whole video on YouTube as well, but I'll see if I can get a screenshot of that last slide as well.
Lovely. Thank you so much. That was super helpful.
Add it up. See you
Thank
around.
you.